Okay, dual port versus single port. We looked at this for you last time, and know that with a single port, maybe the clock rate is a little higher, but with dual ports, there will be no structural conflict for the single pipeline execution. If you want to access at most 2 operands per cycle, okay, there will be no operand access conflict. That's why dual-ported memory, even with slower clock, the speed up is over 1. Okay, so we also looked a little bit at this last time. Suppose we have such an instruction sequence. This is the execution order. So we execute this instruction, and then this, and then this. So if this is the time access in cycle, first clock cycle, we do the fetch of the first instruction. And then in the next cycle, while we're decoding and fetching registers for this instruction, we also fetch the second instruction and so on. Okay, now here's the problem. After a while, after the value of R1 is calculated, we will put it into the register file in the write result stage. And once this register is written into the register file, it can begin to be read by the other instructions. But on the other hand, for this instruction, it wants to fetch operands at this stage. Okay? So why is that? Because this is the source. When does it fetch the source? At stage number 2. Okay? So when it fetches the register still contains the old value, and the data dependency relationship seems wrong. The format is in machine encoding. It could be different, but for the assembly, it's opcode, or I should say operation, destination, source. Okay, this is, we use this order to resemble the mathematical equation. Result is equal to source 1 up source 2. Okay? So result is equal to source 1 up source 2. So as you can see, we will have a wrong source here for this instruction, also a wrong source for this instruction. And for this instruction, there might be chance we can get the right result. And for the final instruction, exclusive OR instruction, there'll be no problem for getting the correct R1. So we use green to show that it is safe, and red to show there might be a hazard, data hazard. So do you get what this FOIL is trying to tell you? Okay, so 3 generic data hazards. Data hazards can be categorized into 3 categories. Category number 1, I want to use your result. That's a true data dependency. Category number 2 is I want to write to the place in where you still haven't read your result. Or maybe I should say it the other way. I want to write my result into the place where you store your source. Okay? So this action should occur after my value has been read by me. If this occurs too soon, then there will be a mistake. So this is not a true dependency, but it may occur. Okay? So we call this what? It's the opposite of the previous case. Let's go back to the previous case. The previous case says, you generate the result and I want your value. So that's a true dependency. We simply call it dependency and ignore the word true. Okay? And this is read after write, or RAW for short. Okay? And this is write after read. Okay? So it's The opposite of the previous case, we call that anti-dependence. The final one is let's go to the next folio. The final one is I want to write that place, you want to write to that place too. But in this instruction execution order, if my place is after yours, then you should write first and then I'll write. Remember, there could be several instructions in between. You may say, such an instruction sequence doesn't make sense. Write and write again. Then what's the use of this result? But in fact, there could be several instructions in between. Okay? So, consider a situation in which our processor can do out-of-order execution. And the mechanism is somehow not that smart, so that it will schedule this instruction to be executed before this one. So timing-wise, maybe we do add here, and then later we do sub. If that should be the case, then after both instructions have been executed, what's left in R1 is the result generated by sub, which will cause a problem. Okay, so we call this output dependence, or simply output dependence. We both want to output to the same location. Okay, so instruction J writes operand. Before I write it, then there will be a mistake. Okay, so the sequence of write matters. Okay, now let's do some analysis. For the true dependency, I do write here, write register at this stage. Yet the value is calculated in the ALU stage. So as you can see, the value is already available at the end of this stage. Okay? When do you need the value? If this is the second instruction. The second instruction says I want to fetch operand at this stage, but really I won't use it until the beginning of the ALU stage. Right? So if there's a way you can let me see your result in time, we can make the pipeline flow smoothly, if there's a way. What is the way? Easy. Run some wires from the ALU output. Remember, this is the ALU for add. The first is add, the second is sub. This uses the ALU to do calculation. This also uses the ALU to do calculation. So the ALU result could be fed to the stage latch, the pipeline latch. Ahead of it, and in the meantime, be fed back to the input of ALU for the second ALU operation to be used as the second source. Okay? How do we do that? Just run wires and then use muxes, multiplexers, MUX, to select the source between the value read from the register file or the value just generated by the ALU. Okay? And in this case, R1 is read out from the register file, and we know that this value is out of date, right? Because a new value has been generated from the ALU output here. So why don't we feed this ALU output also to this ALU input and use a mux to select between the stale data or the newly generated data from this ALU output. Okay? This is called data forwarding. Remember, this ALU is the same as this. So we're feeding the ALU result back to either here, if this value is to be used by the first operand, or here, if it's used by the second operand, and use muxes to make the selection. Got it? It's called data forwarding. And if I can send the data to you for your use in time, then certainly I can do the same to you and to you. So data forwarding is a very effective mechanism. Okay, we are talking about true dependence or simply dependence here. This computer is weird. Next is the anti-dependence. For the anti-dependence, in a single pipeline, first I say single pipeline, and in order pipeline, single and in order pipeline. If it's single pipeline, only one pipeline. If it's in order, in other words, instructions must be executed in order, then the write will always occur at the fifth stage. The read always occurred at the second stage. Plus, this instruction is ahead of this instruction. Then anti-dependence will never be a problem. Will never occur. Okay? Got it? Okay, tell me if in order is a necessary condition. And then tell me if only one single pipeline is a necessary condition. Does it matter if the instruction execution is out of order?
If it's out of order, it will cause a hazard.
Okay, so if it's out of order, then you need to pay attention to the orders of those instructions with anti-dependence. So this is correct. What about single pipeline? Can we have multiple pipelines and still don't need to worry about anti? Correct. Yes, no matter how many pipelines we have running in parallel, maybe 5 instructions in parallel, and then 5 instructions in parallel in the next clock cycle, and then 5. No matter how many pipelines we have, as long as this instruction is ahead of that, then the write always occurs before the read, after the read. Write always occurs after the read, so this is never a concern, even if we have many pipelines. Okay, so I should put an X here, meaning number of pipelines is not a concern. But in order is a concern. Okay? Very difficult to understand. Is it difficult to understand? Draw yourself a picture and then things will become very clear. Okay? So don't do that. Start to put drawing on the paper. Do your little experiments and then you'll find it out. Now, finally, the output dependence. Still the same question. If it's in order execution, and the multiple does it have to be in order? For output dependence, If it's in order, do we need to worry about output dependence? Let me give you the combinations. Single pipeline in order, single pipeline out of order, multiple pipeline in order, multiple pipeline out of order. Which cases don't we need to worry about output dependence? Make your selections.
Multiple pipeline in order.
No output dependence cases. Single pipeline in order. I take? You buy that? Okay. Single pipeline out of order? Of course, no. Multiple pipeline in order? As long as it's in order, do we need to worry about output dependence? Wait. Wait. Multiple instructions are taking place simultaneously. So I want to write, you want to write, everybody wants to write at the same time. So could there be output dependence? Yes, but very simple priority encoder or decoder can solve this problem. If multiple instructions want to write simultaneously, we need to worry about that. But very simple hardware can solve that problem. Okay? And this is, of course, no. Okay, what about if I put a triangle here, meaning the problem is not that serious? Really, the problem here is not that serious. We need to only to do a very simple checking, then we can solve the problem. Same thing happens here. If you know what's going on, then how to solve it, how to deal with it is not a problem. Okay, understand the nature of the problem is the most important thing. So here the author says, we'll see write after read and write after write in more complicated pipes. Okay, forwarding. Here we formally talk about forwarding. The result is generated here and will be latched on the triggering signal of the clock. Okay, and then it's needed here. So as long as we have a path running from here to here, in other words, from here back to here. Remember, the hardware is like this. We duplicate the hardware images to show you how things are happening. Okay, so if you can run the result, run a bus to feed the result back to here or here, then you can forward ALU result back to the next instruction, no matter how it wants to use the source. Okay? For this one, okay, so the ALU output is not needed by this instruction here, but it will be needed when the result is fed forward one more time to here, yet still haven't been written back to the register. So it's still on the fly. The result is still in the air, okay? But it's then needed at this time. So forwarding paths will have to run not just from here back to the sources, but also from here back to the sources. You want to see a hardware picture showing this? Okay, this is the pipeline. 1, 2, 3, 4, 5 stages. For example, the ALU output might be needed by next instruction in the decode and register read phase. Or it might be needed by the next instruction in the decode and register read phase. Or it might be needed by yet another instruction, subsequent instruction in the register read phase. So do we need to do forwarding here? No. Do we need to do forwarding here? Yes. Do we need to do forwarding here? Yes, because in these two cases, the value hasn't been written back to the register file yet. Got it? Okay, so how do we do hardware design? This is memory, instruction memory. We do fetch, and then this is the register file. We do source read. This is ALU. We do computation. This is data memory. We do loads and stores. This is register file. The write operation of the register file, which serves as the final pipeline latch, we do result write back. Okay? So for such kind of hardware, the forwarding path will look like this. From here, ALU output. We need to run a feedback path back to here. Or from the memory stage, if we are not using this stage, then this ALU value, ALU result will be fed forward to this pipe stage, pipe latch, right? So we might need to run this to feed it back to the ALU output again, okay? And eventually, this value will be written back into the register file. Once it's in the register file, we don't need to do any forwarding. For the register file design, no tricks at all. We simply do read at the beginning of the cycle. We simply do read at the beginning of the cycle. And if you want to write, okay, we also do write at the beginning of the cycle. Okay, maybe instruction X wants to read the, what about register R3? Okay, we use R3 for example. If X wants to read register R3, Y wants to write register R3, let's see what happens. R3 will contain some value from the previous calculation, whatever, okay? It will contain some old value. And then, gradually, the new value will be written in. Okay? Gradually, instruction Y will write a new value into R3. Yet, for the instruction X, it starts to do the read from the beginning. It will see the old value, okay? This is the read bus outside the register file, okay? On this bus, instruction X will see some previous trash. And then, gradually, it will begin to see the old value. Okay? Is that what it wants? It doesn't need to know. And then after a while, after register R3 receives the new value, maybe the read bus will have some new changes to reflect the new value of R3. Okay, so the write and read both occur at the same time. And the written result can have enough time to be seen by the read instruction. As long as this point of time occurs before the next trigger, then it's good enough. We're safe. Okay, so it's nothing but a timing issue, but no design tricks needed. So the first half cycle write, second half cycle read is a misconception. Okay, even though you can design such a circuit, but maybe it's not necessary. Question? Okay, we're not done with this yet. So for each of the two ALU input sources, we could receive data from three sources. One is the value read out from the register file. The other is the value fed back from the ALU output. The last one being the value fed back from the memory stage latch. Okay, so there's three possible sources to the ALU input on both sides. What do we do if we have multiple sources to choose among? We use mux. Okay, so let me zoom into this area. We have three sources. How do we make selection? Use a mux. So insert a mux here, insert a mux here to do selection, to do source selection. That's how we do data forwarding. How do you design the control signal? The control signal design is very straightforward. First, you check the instruction sequence to see if this source is equivalent to that source, or this source is equivalent to that source. And then this is really a write operation. For instance, if this is a compare, then this is not a destination. For a compare, we don't write any result back to the register file, right? Or if this is a store, then this is not a destination. A store instruction doesn't have a destined register. Okay, so you need to judge on the instruction type. And then also I need to check on this instruction. If this instruction is a jump, then actually all these are immediate data. The hardware doesn't see these. The hardware only sees zeros and ones, okay? So the hardware needs to be able to identify what operation this instruction is for, and then determine if this field is a source. Got it? Okay, so there are some conditions which need to be met before we do forwarding. Otherwise, we don't do any forwarding. Okay? Worse yet, there could be another source to the second input of ALU. What is that? The immediate, right? Even before forwarding, we already have immediate or register value to choose from. Now, do you understand forwarding? So if in the exam problem, I ask you to list the forwarding control signal equations, can you do that? Can you? If you cannot, raise question. Okay, the control forwarding equation says, if my operation code does generate a result to be written into register, and if my destination value matches either source 1 for this mux control or source 2 for that mux control. And if my operation code does need to read a source from the register file, plus some other nibnaps. I don't know. But do you get the big picture? Got it? So the operation code also gets propagated down for further uses. Okay, at least in here, I need to know whether I want to instruct the ALU to do add or subtract or AND, right? Okay, so hardware change for forwarding. Now you know why we have these muxes. Now you know why we need to... Okay, this is the original design. No forwarding yet. We need to select between the immediate or the register value. We need to select between the register value, or maybe I'm simply doing PC plus 4. I'm sorry, not PC plus 4. PC plus offset for branch destination. Okay, so we already need 2 muxes. With forwarding, my result can come from this ALU output, can come from the ALU output, but yet after another cycle time, or can come from the register, the loaded memory data. Okay, maybe my instruction is a load. And this loaded data is going to be used by the immediately next instruction. Okay? So here, the author shows that we have 1, 2, 3 sources for forwarding, 1 for branch offset, PC relative instruction, and 1 for the plan register value. Similarly, here we have 5 inputs, but this one is immediate instead of the PC plus 4. Okay, and this is the easy part. What's the hard part? How to control them. How to generate the forward control logic. Okay, so these will need to carry out such tasks. Question? Next, with forwarding, the ALU output can be used by next instruction in time, can be used by the next instruction in time, but the loaded result cannot be used by the next instruction in time. For instance, if this one says R4, let's see what happens. If this one says R4, then R4 will be needed here, right? But R4 value will be back into the CPU no earlier than this point of time. No way it can make it. So there will be a 1 cycle stall for such a pipeline design. Okay? So even with forwarding, sometimes we need to have stalls. What about add and then sub, and I have true data dependence? The result of add is going to be used by this subtract instruction. Will there be stalls? Will there ever be stalls? Yes or no? This is a read after write dependence, true dependence. Okay, for true dependence, do we need any stall? Forwarding can be in time, but my answer did not say we're using such a pipeline. The pipeline could be much deeper. So even for such a case, if the pipeline is too deep, stalls are also possible. So data has even with forwarding is if you load R1 in and then want to use R1 immediately, even for the 5-stage pipeline, there can be a stall because you can never make it for the subsource R1. So if you want to get correct execution result, you need to insert a bubble in. And this time we see a horizontal bubble. Remember we see vertical bubble? Basically they're the same. Think about it.
Doesn't that affect the pipeline?
It's just like if this is a traffic flow. You just say stop here and all the cars past this point, please proceed. But all the cars which are behind this point, please wait for 1 second before you proceed. Just like that. Okay, so software scheduling can also help. We talked about hardware approaches. But then in our simple 5-stage pipeline, there's still one case in which the data forwarding cannot help completely. So what can we do further? Like here, if this is the original code, RC is loaded in here and to be used right after. Then perhaps we can put some irrelevant instruction in between this RC pair. Okay. What do I mean by irrelevant? Like this one. This one is not dependent on anyone before it. Okay, so if I move this up to allow for 1 cycle to do the load forwarding, then there will be no stall. Okay, what about here? I have an RF generated by this load and then used by, here. RF generated by this load and used right away by this subsequent instruction. Then I can defer the execution of this instruction by 1 cycle to allow for sufficient time to do load data forwarding. Okay, so with this code sequence, my execution will be bubble, and then bubble, 2 bubbles, 2 vertical bubbles. And for this code sequence, there will be no bubble at all. Speeding up my code.
This would be compiler optimization.
Hardware can do that too. Compiler can do it, hardware can do it. Here, we make an assumption that compiler is doing it. Okay.
For hardware to do it, it would have to be within its block, right?
Okay, if you want to know a little bit about how hardware does this, then let me show you a picture. Up to this point, my machine reads 1 instruction in, executes it, not knowing what's going to follow, right? So if I want to scramble the code, I have no information how I should do that, why I should do that, and how I can do that, right? So if you want hardware to help you out in this case, what you need to do is maybe you need to fetch more instruction in, higher bandwidth, and then put a buffer to record a few more instructions to be executed in the future. And then do examination to see if some instructions execution need to be deferred. Some others can be moved up. Okay? So hardware can also do some checking under condition that I have a higher fetch bandwidth. on the condition that I have a space to buffer some future instructions. Okay? Now you understand why we need to have an instruction window. Okay, a window is sometimes, I'm sorry, an instruction window is a buffer in nature. And the reason we need to have a buffer this is sourcing side. This is the consuming side. When do we need to have a buffer? When the speeds of the two sides are imbalanced, or the speeds of both sides need to be balanced. If the speeds of both sides are imbalanced, suppose this side produces the material faster, and this side consumes the material slower. Tell me what will happen. No buffer can ever help. It will always explode, right? So the speeds need to be balanced. But if the speeds are not smooth, sometimes it generates material faster, sometimes it consumes material faster. Can the buffer help? Yes, buffer only helps in such a case. Okay, now you understand why we need a buffer. So, in another case, when the sourcing side is slower and the consuming side is faster, this time you see the buffer will not explode. So, will a buffer help now? No need for it. Okay? Only when the speeds are not very smooth, but in the long run, they should be balanced, can the buffer be of any help. Maybe you all have wrong idea about the buffer before, but now do you understand when we should use a buffer? Okay? So with a buffer, the speed should be balanced. Or if this side, the sourcing side, is faster, then whenever the buffer is full, the sourcing side will be blocked, eventually making the speeds balanced. Even you can run faster, you cannot. Control hazard. Next topic is control hazard. The control hazard says if I have such an instruction sequence, instruction I plus 1, I plus 2, I plus 3, but unfortunately this instruction, this branch will be taken, so the next instruction is no more I plus 4, but target address. And in this case, these three instructions should not have been executed at all. Okay? Unfortunately, they're already in the pipeline. Half alive, half dead. What do you need to do? Kill them. How do you kill an instruction? Tell me, how do you kill an instruction? With a knife, pistol, or simply disable its write to the register file. Choose one. Okay, so don't let it change any condition code. Don't let it change any memory. Don't let it change any register. That's the easy way to kill it. Okay, when do you change register? Here, it's easy to kill. Just kill wherever you want to kill it. Just kill the corresponding read register file enable signal. Okay? Whenever you want to kill a store instruction, kill the write memory enable. And if you don't want to change any register file, you need to do it no later than this stage. Don't let it set the flags. no matter what happens in the operation. Okay, now you know how to kill? Easy. So if that's the case, then we have a control hazard. So what we need to do is we want to properly invalidate the execution of these 3 instructions. Let's look at the hardware. The hardware says, it's that diagram. But anyway, okay, 5 pipe stages. Okay, so you read registers out from here. And our branch F allows only one condition check, which is equal or not. So I do equal check. Is equal check easy? Exclusive OR, and that's it. Okay, so it can be done very, very fast in the same stage as the register reads. Okay, that's MIPS design. It wants this to be resolved quickly. And then use the ALU to do PC plus 4 plus offset at this stage. Okay, when do we know whether we want to branch or not? Here, after we do the check. When do we know where we should go if we want to branch? Here, after we do PC plus 4 plus offset. Okay, when do you want to kill the subsequent instructions? You can do it here. Because if you want to jump, then the value of the target doesn't matter. You want to kill your little brothers and sisters anyway. If you have more routes to send data to proper places. That's why CPU, inside of CPU, it's packed with wires everywhere. Okay, because everybody wants to get the first-hand information. It can be done in the ALU if you want to have more complicated comparison, like greater than, positive, whatever. Okay. But if only equal or not, it's easy. So if you want to see if it's 0, compare it with R0, which contains 0 all the time. If you want to base your branch on the condition of whether 2 register values are equal, no matter what registers you want to use, a comparator with exclusive ORs can do that. Okay, so that's control hazard. And we need to do something about these 3 instructions. Let's go on, although I already tell you what to do. What do you do with the 3 instructions in between? How do you do it? Where's the commit? Commit means what permanent changes have been made. Okay? So my simpler question will be, what do you mean by permanent changes? Okay, the answer is the register file can keep your permanent change. Data memory can keep your permanent change. Condition flags can keep your permanent change. Just don't touch those things. Then there will be no harm. Okay? Okay, branch star impact. Now, everything has been taken care of properly. We are safe. But then what? Tell me then what? We lost 3 cycles. Okay, 3 cycles are non-productive. How bad is this? Well, to answer this question, then we need to know the frequency of branch instructions. Branch instructions will be encountered in every 5 to 6 instructions during execution. So for every 5 or 6 instructions, let's take 5 for example. 5 instructions, according to our naive conception, 5 instructions will take 5 cycles, right? But if this branch wants to branch, then we lose 3 cycles, right? So 5 cycles becomes 8 cycles occasionally. How occasional? Well, up to between 70 and 80% of the branches will really branch. Okay? The most obvious example being the final branch check of a loop. It almost always branches. Okay? So between 70 and 80% of the branches will really branch. So my equation becomes 5 cycles becomes 5 plus 3 times 70 to 80%. The result being more than 7 cycles. My processor gets slower. Okay, how do we speed it up? By eliminating this waste, right? Tell me how you can eliminate this waste. By guessing. We looked at one technique called the delayed branch. And I told you delayed branch is no good. I told you guessing can be 98% correct easily. Okay? How can that happen? First, you have to be accurate. Secondly, you have to be fast. Don't take too much time to ponder, to think, to make your guesses. No way you have only 1 cycle to make decision. More than 3 cycles, nobody wants your answer. Because I already know the truth, I don't need to guess the answer. Okay, so how can we guess in 1 cycle and yet still be so accurate? Somebody tell me. How can we do that? How can that be possible? Okay, now let me give you the answer. First, I need to design my instruction set architecture properly. Why does it have to do with that? Okay, that's because all my branch instructions has the target PC plus 4 plus offset. You see, all the branch instructions have this target. What is PC plus 4? Oh, its location when it's loaded into the main memory for execution. Its location is fixed. Okay? So this is a constant to me. During execution, it's already a constant. What's offset? Oh, it's written in the instruction, so it's another constant to me. So constant plus constant, the value will never change. I solved one question. That is, for any branch instruction, its target never changes. If I can use a table to record its target, once the target has been calculated, I can use it forever. Okay, that's question number 1. So my target can be predicted, guessed, 100% correct. Next is the if condition. How do I guess the if? It's a little harder, but not that hard. Because in a program, most branches tend to have the same behavior. Either very unpredictable, which are the rare cases, or very, very predictable, which are the usual cases. With all this information, do you think guessing branches is easy? Okay, so what we need to do is how to do it fast. By now, we know it's easy to guess, but how to guess it fast? The way to guess it fast is, sorry, I'm not following the foils. Do you think this way of lecturing is okay with you? You want to know how to do it fast? Okay, very easy. I use a table. This table is like a hash table or cache. You understand cache or hash table? Which example do you want me to use? Cache, okay? I use a cache as an example. So whenever I see a branch, I say, okay, this is branch A. I have a space for it. Its target has been calculated. I record it here. And then this is the history of its behavior. Okay, I use this to do taken or not taken prediction. Okay, so I call this target buffer. I call this branch predictor. Really, my prediction needs to do this part only. This part is no more prediction. It's a fixed fact. Okay? And whenever instruction memory, whenever I send PC in to fetch instruction memory, I want to fetch the instruction right. I also send the PC to this table to do tag match or indexing, whatever way. Anyway, then I can find out whether I have branch A information recorded or not. So when the branch A is fetched into the instruction register, I also have this target available, right? This is cache. This is also a cache. This is a 32 kilobyte cache. This could even be smaller, faster. Okay? So I fetch instruction out from here. I fetch target and prediction information out from there. So when I put the branch instruction into the instruction register, I also use the predictor information to put either PC plus 4 or PC plus 4 plus target into my PC register. You see, when I load the instruction register with the new instruction, which is branch A, I also, in the meantime, have decided where to fetch the next instruction. If my guess is this one, then this one will be fetched in here. No delay at all. You see how we can do it fast? First time, maybe we'll miss it. First time, even though we guess it's a taken branch, we still don't have the target. So we can only wait. But after the first time, 98%, I put my correct next instruction right here with no penalty. Okay, the guess is correct. Okay, I update this information saying more confidence. If the correct is if the guess is however incorrect, then I update my information here saying less confident. Okay, that's how we deal with branch instructions. Okay, so do you understand what you need to do with the 3 instructions in between and how you do it and where is the commit point of every different type of instructions? Okay, branch style impact. Now, if 30% of the instructions are branches, in fact, 20% between 20 and 30%. And every time we encounter a branch, we need to encounter a taken branch. We need to stop for 3 cycles. So the new cycles per instruction will become 1.9. It's similar to my calculation here. Okay. So 2-part solution. Determine branch taken or not sooner and compute target address earlier. Both will have to be done before you can proceed. And MIPS branch test if register is equal to 0 or not 0 only. It doesn't allow other type of tests. Okay, so the work begins with the instruction set architecture design. Now you begin to appreciate why we emphasize instruction set architecture will have to be designed carefully. Okay. And MIPS solution is move 0 test to earlier stage, as I said. If it's a very simple equal or not equal test, it can be very easy. If it's a 0 test only, it's even easier, just a big NOR gate. Okay? And adder to calculate new PC plus 4 plus offset, and 1 clock cycle penalty will be needed. Only then. Okay, what does it mean? Do you see what this means? This means, remember we have a ALU here. Okay? We need yet another adder, a new adder, extra adder to do the calculation instead of using the regular ALU. So this adder, since it's additional, it can be used at any cycle. Okay, whenever you want to use it. Okay, so the equal or not equal to 0 comparison is done here. The target calculation is also done in here. We can move the result resolution up by 1 clock cycle. So you see this, you see this. And you understand why we should design instruction set carefully and add hardware and properly calculate cycle time. Everything's in one. It's a complete solution. Okay, so here we may have different alternatives in handling branches. Number 1 is to stall until branch direction is clear. Like in the previous FOIL case, we wait until we know whether we need to branch and then kill the instructions if necessary. This is the stall solution. The second is to predict branch as not taken. In fact, the stall solution is almost identical to predicting not taken because you just keep fetching the subsequent fall-through instructions, like you're predicting that the branch will not be taken. So execute successive instructions in sequence and squash invalidate instructions in pipeline if branch actually taken. An advantage of late pipeline state update, since all the final updates will occur only at the end of the pipeline. It is easy to invalidate instructions. And according to the author's benchmarking, 47% of MIPS branches are not taken on average. But as I told you, maybe only 20 to 30% are not taken. The rest are taken. And PC plus 4 already calculated in first cycle. So use it to get next instruction. Use it to get next instruction means to execute successor instructions. Alternative number 3, branch are predicted taken. Since this is the majority behavior of the branch instructions. But without the target address, such a prediction would be useless. So the target calculation will have to be moved up to the earlier stages of the pipeline. So if you predict it to be taken, there will be some cycle penalty. If you predict it to be not taken, there will be no cycle penalty at all.
So the penalty is to basically do that, right?
No, without that. If you want to calculate the target address, the best you can do is to do that during the decode. Okay, so there's already one cycle penalty. And number 4 is to use delayed branch. We talked about this previously, so I'll skip this part. Okay, so you have any questions so far? Okay, let's talk more about branches. How many types of branch instructions do you know of? Let me repeat my question but rephrase it. How many types of instructions will change the control flow? Which types? Branch if is one type. Jump is one type. Conditional, unconditional are both of these categories. Unconditional is just a subcategory. What else? Return. What else? With the return, then the call should come to your mind. Okay, so there's a call. Okay, this one always have a fixed target. Jump always have a fixed target. And this is always. Okay, so it's also a subcategory of this, even though MIPS says this is of another instruction type. So these two can be treated the same. What about return? Return always returns to different places. Wherever you call me, I return to your +4. Okay, so return doesn't have a fixed target. Call is weird. It has a fixed target, but with return point, right? Call will also provide you with a return point. So how do you deal with call? You can deal with a call similarly with this. Plus, you need to have a place to store, to remember the return point. Okay? Then what about the return? Return can also be treated similarly with something different. The target. Don't pay attention to the target in here, because the previous target, the last target, is not the target I'm going to use this time. I'm called by somebody else. I need to return to its +4. Okay, so return retrieves its target from the return buffer. Okay, do you allow for nested calls, like in a recursive case? Like in the nested case in general? Yes, then whenever you encounter a call, push its return point into this buffer. Another call, yet another call, more calls, doesn't matter. Because all the returns will be in a non-order, reverse order, right? Okay, so this buffer better be arranged like a stack. In fact, it's a stack. Okay, so whenever I encounter a return, I pop the stack. Whenever I encounter a call, I push the stack. And things will never go wrong unless there is a stack overflow. because for Hanai Tower, I may call millions of times. Okay, so the Stack Overflow problem will need to be properly handled. And now you know all the methods to deal with all kinds of control flow instructions. Any further question? Okay, delayed branch, I'll skip it. Okay. From before branch, this is the safest method. From branch target, this is the second best, and you should be able to squash these instructions because your guess may be wrong. Okay. And from fall through, both need to have the squash. Squash mechanism. So A is the best choice, fills delay slot and reduces instruction count. In B, when you move the instruction in from the target, be very careful not to make your program cause any mistake, because this can be the target of this branch, but it can also be the target of other branches. So the code should remain the same. Yet, if this instruction sequence follows this branch, then this should not be executed anymore. Shouldn't be executed twice. What do you need to do? As long as you know such a problem, you know how to deal with it. So I'll not elaborate on this anymore. Okay? Okay, same thing happens here. Compiler effectiveness for single branch delay slot. It has 60% of chance to fill one delay slot. And 80% of this filled instruction can be useful. So 60 times 80 is about half of the probability it can be of use. Okay, it also has downside, and you read these through on your own. Okay, so evaluating branch alternatives, these are just equations and some examples. We have 4 alternatives. Each one has this branch penalty, and the CPI will become this. So which is the best method? This may be the best choice. But as the pipeline gets deeper and deeper, the number of slots to be filled becomes more and more. Like for a 20th stage pipeline, there may be 10 slots for you to fill. So as the pipeline gets deeper, or the number of pipelines gets more, people begin to dislike this method. Too many slots to fill. Okay? So currently, a prediction wins. And the prediction is not a fixed direction prediction. The predictions are the flexible predictions. The flexible predictions win these days. What's the advantage of stall pipeline? There must be some advantages. What is it? Simple design. Good for stupid students. Okay, there are other problems with pipelining other than those we already talked about. So we're entering into a new topic. The other problems include exception, interrupt. What is an exception and what is an interrupt? Are they different? Well, maybe or maybe not. Some companies call hardware incurred conditions exception. Yet, Some other companies call such exceptions interrupts. Okay, these two terms are used interchangeably or differently by different companies. So why don't we call them exception in general? Okay, anyway, exceptions. Let's see how exceptions can be handled. As a very important principle, whenever you handle an instruction, whenever you handle an exception, you must restart your program execution at the proper point. You must know where to restart it and restart it completely faultless. Okay, because at this point of time, it's very easy to make mistakes, all kinds. If this is a pipeline, and if I have an exception request coming from the outside, it could happen anytime, right? But I'll use clock signal to record it, recognize, and assume that it happens, gets recognized at the end of a clock cycle. So if there's an external request, and this request is so important that you are going to handle it, what do you do now? Some people say, abandoned. Discard everything which has already been partially done. I don't want any of these instructions. I'll finish execution. This instruction execution has already been finished. Okay, I squash all the other instructions. Some people say, no, it would be a waste because this is 80% done, 90% done. So maybe I'll finish all those which are maybe more than 60% done, but squash the rest. And then some other people argue that your exception handling response time has been delayed by some cycles, too slow. Okay? So some other people say, maybe I record all this information, and after servicing the exception request, I start from here. Then you need to have big memory. You need to take time to record things down. Also a kind of disadvantage. So what do? Different companies use different approaches. No standard answer. Okay, it's all up to you. And customers determine whether your design is good or not. Some says it's during execution by the instructions, so it's somewhat software cost, somewhat hardware cost from external, asynchronous, could occur anytime. But anyway, it must appear that the execution of interrupt must appear between two instructions. So whatever, you will have to stop at the end of instruction I, do interrupt handling, and then resume execution from instruction J, or I+1 rather. Okay, you must preserve such an execution image, however you did that. Okay, so in order to handle such cases, let's see, we have external interrupt requests. We also have internal. Let's look at the internal cases. Can we have instruction memory fetch interrupt? Can we? Is it possible? The answer is yes, page fault. Or if this is from a cache miss. Okay, so there are interrupts. Okay, usually for a cache miss, we simply wait. Usually for a page fault, we simply switch context. Why? Why do we simply wait for a cache miss? Why? Okay, number one, cache miss turnaround time is short. From a few cycles to a few hundred cycles. Okay, the worst case would be going into the main memory. Okay? Secondly, if upon a cache miss you want to switch context, tell me what happens. Whenever you switch context, you will have cache miss. Plus you abandoned the contents of cache completely. The previous contents completely. Do you think that's smart? Okay, that's why we wait on cache misses. Okay, so you understand why we wait on cache misses. Then why don't we wait on page faults? Because this guy just told me things will eventually settle down. Right? Why don't we wait on page misses?
Take too long?
Takes way too long. Tell me how long. Tell me how long. Million seconds to access the disk. Right? Page miss will have to access the disk. Plus move data around. So millis of seconds. In other words, millis of seconds. Now we're running at gigahertz speed. Millions, tens of millions of instructions can be executed during this time. Tens of millions of instructions can be executed. Would you want to waste the time interval, or would you rather do something else? Tell me. You want to wait? You want to proceed with some other tasks? Yes. Why? I always ask you why. Because the context switch also takes time. You see, you return control back to the OS. OS saves your state. OS loads in other programs. OS starts to run these programs. How long would that take? And this procedure will have to repeat it again when you want to come back to resume execution. So how many cycles would that take? If you don't have that knowledge, you don't know how to make decision. Agree with me? Usually kilos of cycles at least. Okay. For the lightest weight OS, kilos of cycles to do context switch. But could be up to millions of cycles. But if we're talking about gigas of cycles of waste, then it's still worth it. Okay, now you understand why we wait or we don't wait. Another question is, who handles cache misses? The answer is hardware, right? Because any software intervention is like a context switch. No need, no time for that. Who handles page fault? Hardware can do that too. But page fault is already a task which is handled by the OS. Plus, we have long enough time to do things more carefully, to select which task to be scheduled in. Okay, so we want to do optimum solution at this time. We let OS to do it because software, we can think of software as being smarter than the hardware, more considerate than the hardware. Okay, so we let software to do it. Make sense? I want this to be your knowledge. Don't just memorize it, but don't know why. Okay. Okay, so let's look at the pipeline. When can we have exceptions? Cache miss. When can we have exception here? illegal opcode. When can we have exception here? Overflow equal to 0, whatever we want to detect. When can we have exception here? Similar to the instruction memory. Okay. When can we have exception here? Never. Because the register field always contains a certain number of bits, and whatever bit pattern, there's one correct interpretation to this bit pattern. Okay, always a reasonable interpretation to the bit pattern. Okay, so there's no exception possible. Or we can have external asynchronous interrupts coming from the outside. So if there's an interrupt here, what do we do? Handle it. Or wait. Tell me what? When there's an interrupt here, tell me if I should handle it or I should wait. Handle it. I said, I should. In other words, there's one correct way and the other way is incorrect. Okay? It's not an option. I'll have to handle it right away or I'll have to wait. Tell me which one is right. Okay, let me tell you what I'll do. I'll wait. Why would I wait? The reason is obvious. Which is the oldest instruction? Old. It has been executed for quite some time. And this has just been fetched in, right? So you know which one is the oldest. Now I see an interrupt. Decode the interrupt. Should I handle this interrupt? No. Why not? Because from this point of time and up, maybe I will have an overflow interrupt here. Maybe I'll have a memory interrupt here. If I eventually have these three interrupts, which one should I really want to handle first? Tell me. The one caused by the older instruction, by the oldest instruction. So I need to handle this first. And if handle this first, the whole thing could be in vain, useless. You wasted a lot of time doing no good job. Okay? By handling this first, maybe this will go away. Maybe this will not happen again. Okay? So now you know whether we should wait or do it right away. You tell me. Okay? Got it? Good. So that's why if there's an interrupt, I want to wait until here, then I do interrupt resolution and determine if I have multiple interrupts observed, which one I should handle first. So even if I see an interrupt, I'll let the instruction to continue going on. Let it go. Continue to do wrong things because I cannot handle it yet. And in conclusion, okay, nothing important here. It simply tells you, after I dismiss the class, when you go home, you need to do reading. You need to review what you have learned. Things are never so easy. Okay? If you do well in this class, is that enough? No. You need to compete with all the students, all the graduate students worldwide. And now let's look at the performance advancements in CPU designs and memory designs as the time goes. So from 1980, a long time, CPU speed up is like this. Why so steep a curve? Why is that? Because we did understand how to design better computers to the CPUs, I should say CPUs. Computer includes everything, including the metal chassis and the color of your notebook. Okay, we did know how to design CPU in accordance with the available state-of-the-art technologies. Okay, like we have numerous transistors to use, so we can pipeline it. Okay, we have numerous transistors to use, so we can put caches on the same die and whatever. Okay, so the caches may be considered part of the CPU starting from 1970. Okay, starting from 1980s, on-chip cache is a norm. Almost every product, high-end product, has on-chip caches. Nowadays, we even have 2 levels of huge caches. Okay, so from IC technology advancements to risk revolution to deeper and deeper pipelining, and also IC technology advancements all the time, continuously until today. Moore's law is not dead, according to Intel. Okay, but for the memory part, the speed advancement is relatively very slow, and I told you the reason. Now, somebody want to repeat it for the class? Why is the memory speed increase so relatively slowly? Somebody tell me? The answer is very easy. The die gets bigger, okay? And the density gets higher. So maybe the capacity is orders higher than previous. But for the memory access, it is not pipelined. The wires gets even longer. So if I don't see speed decrease, I'm already lucky enough, right? Because basically it depends on the wire delay. We can, on the contrary, still see speed up. We're really lucky enough. Okay, so we have a 6 to 8% speed increase per year, yet we have almost 50 to 60% speed increase per year for the CPU. As a result, memory gets further and further away from the CPU. In other words, memory is relatively becomes slower and slower as the time goes. Okay? Is that tolerable? Impossible. All the CPU speed will be eaten up by the slow memory. So we need to do something. And that something is hierarchical memory design. Long time back, the memory was faster than the CPU because the memory logic is very straightforward, and the CPU logic is very complicated, incurring all kinds of delays, plus every instruction may take multiple cycles. Okay, so long time back, CPU is slower, but today the story is different, and we have looked at this before. And for the Apple iMac G5, the memory hierarchy specification is like this. Not important. Okay, this may be important. Why is this managed by what? There are reasons behind this. Okay, always have a system view of everything, even if you are just writing a program. Okay, if you want to respond to an email, don't simply say reply. Say reply and maybe delete the previous email to save some internet bandwidth. Leaving maybe only a few keywords. Dinner tomorrow? Dinner together tomorrow? Just leave that. and delete your loving Anne, your loving Mary. Delete that part. Okay. And this is the CPU design. You can see register files here, caches are here, and this is a level 2 cache. Okay, and maybe for today, the level 2 cache real estate constitute about half of the chip area. Okay, things are changing all the time. And what makes memory, hierarchical memory or memory system design effective? Only one reason behind that: locality. Locality, there are two kinds of localities. One is temporal, meaning if something is used now, it should be used very soon again. And spatial locality means if a piece of information is used now, then very likely its neighboring pieces of information will be used very soon. Okay? So based on these two, we survived for decades in memory system designs based only on locality for the overall speed. It is a property of programs which is exploited in machine design, and this property comes very naturally. But it can be enhanced by you as a programmer or by you as a compiler writer. Okay? Okay. We need evidences. You tell me programs have locality. Show me. I want to see the fact. So this is the fact. This is the time axis, and this is the addresses. Addresses, okay? Like address 0, address 100, address 1000, okay? So this location will be accessed almost constantly a long time. Do you think this thing has a very good locality? Yes, it has self-locality. And if you care about temporal locality, right? When talking about temporal locality, we focus only on individual pieces of information. That's my so-called self-locality. Okay, very good temporal locality. You want to see spatial locality? Yes, all the neighboring locations are used almost within time window. How do you define time window? Maybe thousands of cycles, depending on how large your cache is. If you have larger cache, then your time window can be enlarged. Okay. Anyway, don't incur too many misses. Then I can call that within the time window. Okay. You want to see bad locality? Tell me where I can find bad locality example in this diagram. Okay, like the individual dots. Individual dots show very bad locality. Any other cases? Like this tilted line. It may look like it's having some spatial locality, but not too useful. Okay? Maybe you have fill-in a cache line, but after a few cycles you will have a miss. Okay, so a tilted line shows bad locality. Individual dots show bad locality, and some others like the short line may also show bad locality, at least not too good locality. And this locality is almost perfect. This area is super. Okay, now you know how to see the diagram. Run your benchmark, plot the similar diagram, and you very likely will see the same phenomenon. Temporal locality. spatial locality. These two are not the good cases. This is an even better spatial locality. And bad locality. And individual dots are worse. So terminology, hit, you understand what hit means. Hit is represented in percentage form. No, I'm sorry. Hit means you found it in certain hierarchy. And with many number of accesses, you will begin to be able to calculate hit rate, miss rate. And hit time is important. Now you understand why it's important. And miss penalty is the miss time minus the hit time. Okay, the extra part is called penalty. Remember, if you walk away with a bottle of water and the fine is 50%, eventually after you pay the fine, do you own the water? No. So it's simply the penalty. Okay, and I also need to introduce another term to you, the inclusion property. Inclusion, something is included in others. In memory hierarchy, usually we require that all the hierarchies, its information, its content is included in the lower level, is included in the lower level, is included in the lower level. With this, it's easier to do what? If it's included, it's easier to do what? Data consistency. Okay? Whenever I get a new copy, it's easy for me to inform my one level down memory system. Okay? And then it becomes your responsibility to update your next level when appropriate, like when page faults. Okay? So the inclusion property is very key to memory system design. It makes things much easier. Does it waste a lot of space? Because the information is duplicated so many times in every hierarchy. If you think that's a big waste, raise your hand. I need to keep only one copy. But now you want me to keep n copies. You think that's too wasteful? Then raise your hand. No. Once it's in the upper level, I can discard the copies in the lower levels to save space, to let more information in.
But you have more space.
More space, right, then I can have more available space. So you think that's a waste? You don't think that's a waste? I'm only talking about the efficiency of the space. Give me your wallet. I need to fine you for 1,000th of what you have in the wallet. Is that okay with you? 1,000th. Is that okay with you? Not too bad. So, 1,000th of this hierarchy's capacity. 1,000th of this hierarchy's capacity, 1,000th, 1,000th, 1,000th. So the waste is really not that bad. Plus, it makes things much easier. Okay, so don't worry too much about inclusion property. It's a good thing. Okay? That guy is very stingy, only 1,000th. And he says no. Yeah, that's all right. I understand. His wife is watching. Questions? Okay, so inclusion property, remember this. So is everything in here included in the cache? Oh, no, this time, no inclusion property. Okay, no more. Okay, because we generate new value in here and update cache only when I do store. So when looking at the interface between these two hierarchies, it becomes a programming style issue. Okay, we don't need to make decision. We don't need to worry about this. Okay. Okay, so we look at this before. No, we haven't. So hit rate, you already understand that. And average memory access time is the hit time plus miss rate times miss penalty. And this miss penalty could propagate to lower levels. So be very careful. What is this miss penalty? Expand this term into hit time of the next level plus miss rate times miss penalty of this level. Okay, I got another miss penalty. Expand the term again recursively until you get down to the lowest level at which you can find your information. Okay? So miss penalty for the lowest disk level, it includes the access time and transfer time. Well, for every level, this is true for every level. Okay, so for every memory hierarchy, every individual memory hierarchy, we need to ask some questions. Question number one, block placement. Where can I place it? Tell me, where can I place a page in my memory? I have a disk, and then I have a DRAM in memory. DRAM is not equivalent to my memory, but it's accustomed that when we say DRAM, we mean my memory. Okay, so where can we place a page in my memory? Where? The answer is anywhere, and OS decides it. Okay, how come it can be anywhere? Oh, okay, so we divide our information into fixed-sized chunks called pages, and also divide our memory into fixed-sized spaces called page frames. It's just like 3x5 pictures. In the picture album, every picture can fit into any space. Very easy management. The only question left is where to place it. Okay, anywhere is okay. Okay, so OS chooses a free page frame or replaces the least useful page already in the page frame. Okay, so this is placement. Next is identification. Okay, now we're in a bad situation. A page can be placed anywhere. Where can you find it? Where can you find it? Number one, there's a way to calculate the location of it, but that's not too flexible. Number two, it can be anywhere. I need to search through the whole space. That's more flexible. Which one do you want to use? Well, the answer depends. For the page management, we want the flexibility to be as high as possible. Why? Because page fault cost is too high. I want to do my best to avoid any page fault. So I want the best placement. The best placement is what? Random. Full freedom. Okay? So how to identify where it is? If it's random, then the only scheme may be table lookup. Okay, I'll pause here. Maybe let me finish these two too. Okay, so what if it's full? If it's random, then I need to find the bad candidates, choose the worst among them, and replace it. Okay? So whenever there's flexibility, replacement becomes an issue. You need to make right choice. Okay, and the last is write strategy. Write strategy says whenever I want to write an upper hierarchy, does the write need to go through to lower hierarchies? Yes or no? Well, there are certain considerations which we'll talk about later.